Word search 2, you get a grid and many words. Return every word you can spell by moving up, down, left, or right without reusing a cell on that path. In example 1, eat and oath work, pea and rain do not. Second example, a 2x2 board with A, B, C, D, the only word is ABCB, but you cannot spell that without revisiting a cell, so the correct output is an empty list. If we run a separate search for every word in the list, we keep redoing the same first steps from the same starting cell. That is redundant, and it does not scale when the dictionary has hundreds or thousands of words. Instead of one hunt per word, we keep a tree of the whole dictionary. As we move on the board, we move through the tree. It is a map of every valid prefix. If the next letter is not a child of the current node, no word in the list can match along that extension, so we stop exploring that branch. When the board spells app, the tree node for app may already be a complete word, and it also has a child for L that leads to apple and apply with only a couple more letters. One walk is carrying the whole dictionary along shared prefixes. Suppose we try to extend with Z. The tree node after app has no child labeled Z, so no word in the list can match that move. We back off immediately. That pruning is what keeps the search fast in practice. Instead of carrying a string index in depth first search, we pass the tree node that encodes the prefix matched so far. Each step on the grid follows a child edge in the tree. The board cursor and the tree cursor stay in lockstep. Step through A, then P, then P. The tree lands on a node that is a full word, we record app. Unlike classic word search for one target string, we do not stop here. If this node still has more children, we can keep walking to longer words such as apple. We still mark visited cells on the current path, often by temporarily replacing the letter with a sentinel such as a hash. That is the usual board search rule. Along one path, each physical cell can be used at most once. We have already spelled apple on the board. Many implementations prune the tree now, clear the word flag at the leaf or remove the leaf so we never emit the same word twice. If a node loses all children, delete it on unwind. Here the branch that ends in E for apple disappears after we add apple to the answer list. If the next letter on the board is not a child of the current tree node, the recursion stops right away. We are not merely failing one candidate string, we are ruling out every dictionary word that would have needed that extension next. M and N are the board dimensions. S is the total number of characters across all words, and L is the maximum word length. Time is O of M times N times 4 to the L plus S in the worst case, S to build the tree, and M times N times 4 to the L for depth first search from every cell, with at most 4 neighbor directions per step. The tree prunes impossible next letters, so practice is often better. Space is O of S for tree nodes plus O of L for the recursion stack. If you mutate the board with a hash mask and restore, extra space beyond the stack is constant. Part 1, Find Words is the main entry. It builds a tree using insert, then loops over every grid cell and calls DFS with the tree root. The answer list is shared across those calls. The next beat zooms into DFS, which uses the tree you just built. Part 2, this is the helper that Find Words calls for every starting cell with the root node. At each step, follow the tree child for the board letter. If there is no child, return immediately. When the node marks the end of a dictionary word, record it and optionally prune, remove the word at the leaf, then delete tree nodes that have no children left, walking upward. Hash the cell, recurs to 4 neighbors with the child node, then restore the letter.